This section we're going to learn how to find out the mass percent from the chemical formula. Okay, so mass percent of element X you can find out by doing this formula, which is atoms of X in formula times the atomic mass of X. The number of atoms times the atomic mass, and you divide it by the mass of the whole compound times 100 will give you the percentage of mass percent in the element X. Okay, that is the atomic mass of X. And similarly, you can use this formula where the number of moles of X in the formula times the molar mass. If you know the number of moles and you multiply it by the molar mass of the X and you divide by mass of 1 mole of compound. Basically, they both of these are similar. Okay, we will look at this with some examples. The first example, it's asking ammonium nitrate is a common fertilizer. What is the mass percent of each element in ammonium nitrate? Okay, so what is the first thing that we need to do? We need to first find out what is the formula for ammonium nitrate. So let's go ahead and write the formula for ammonium nitrate. Ammonium ion is +1 charge, and nitrate, from your polyatomic ion table, you will see nitrate is -1, ammonium is +1. So when we put it together, it's going to be 1:1 ratio. That would be ammonium nitrate. That's the formula. Okay, we want to find out the mass percent of each element, meaning what is the percentage of nitrogen. So the nitrogen percentage would be, there are 2 nitrogens, 2 times the mass of nitrogen, and you divide by the molar mass of ammonium nitrate. Okay, and then you multiply it by 100. So the percentage of nitrogen would be 2 times the mass of nitrogen, and then you divide by the molar mass of ammonium nitrate. So we know that we need to find out the molar mass of ammonium nitrate, which you guys know how to do now. There are 2 nitrogens, 4 hydrogens and 3 oxygens. So if you find the molar mass, calculating the molar mass of 1 mole of ammonium nitrate, there are 2 nitrogen moles, 4 hydrogen, 3 oxygen, and use the molar masses of them. You know how to do this part now already, and that would be 80.05 grams per mole. That is the mass of the whole compound. Okay, so what would be the percentage of nitrogen in it then? So if you take 1 mole of ammonium nitrate, there are 2 moles of nitrogen. So the percentage of nitrogen would be, there are 2 nitrogen. What's the mass of each nitrogen? 14 times 2, 28. Right? So 2/14, and you divide by 80.05 grams. That is the mass of the whole compound, and you multiply by 100. That will give us the percentage of nitrogen. Easy. How do you find the percentage of hydrogen? So there are 4 hydrogens, right? So you use that like this, you see. 28 grams divided by 80, and then you multiply by 100. That would be 35% mass percent nitrogen. Mass percent of hydrogen would be number of moles of hydrogen. There are 4. Molar mass of 1 hydrogen, 1.008 grams per 1 mole. And then mass of 1 mole of ammonium nitrate, 80.05 times 100, 5.037. Similarly, we can find out the mass percent of oxygen. So in ammonium nitrate, there are 3 oxygens, right? So you multiply 3 times 16, 3 times 16, and you divide by 80, which is the mass of ammonium nitrate, times 100. So that will give you mass percent of oxygen. If you add up this 59.96 and 5.0 5.037 over here, and also if you add up 35, they all should adds up to 100%. Okay. Okay, that is how you find out percentage of element in a compound, elements in a compound, and mass fraction and the mass of an element. Mass fraction can also be used to calculate the mass of a particular element in any mass of a compound. Okay, let's say you are given a certain mass of a compound and you want to find out the mass of any element in the sample. Simply you take the mass of the compound that is given and you use the same ratio like we did before, that is mass of 1 mole of compound would be your denominator, and then mass of element in 1 mole of compound would be in your numerator. Let's look at some examples so you'll understand this. Use the information from sample problem 3.6 to determine the mass of nitrogen in 650 gram of ammonium nitrate. Now it is the same problem that we did earlier. It's talking about ammonium nitrate. So you know the mass of ammonium nitrate already because we calculated that. Okay. So we are given the mass as 650 grams. So we can use the same ratio as before. So we are given 650 gram sample. So you write the mass of the sample, and then in ammonium nitrate, remember we know how to do the formula. Also we found the mass of ammonium nitrate, which is 80.05 grams. Ammonium nitrate, and in this one there are 2 nitrogen, so each nitrogen is 14, so 14 times 2 is 28. So the mass of nitrogen in 650 gram is, so this ratio 28 grams per 80 doesn't change, so you use this formula, use the 650 and then 80.05 gram, you have 28 grams, so you do this calculation and will give us the mass of nitrogen in 650 grams. That's easy. Okay, earlier we put the percentage mark here without this part, but now you don't need to use the percentage because you are not looking at the percentage. Instead we are looking at the mass. Okay. Okay, here the same thing that I just talked about. Mass of the ammonium nitrate given, and then the mass of 1 mole of ammonium nitrate 80 grams, and then 2 moles of nitrogen 28, so 228 grams. Okay. Okay. So another important concept is empirical and molecular formulas. Empirical formula is the simplest formula for a compound that agrees with the elemental analysis. It shows the lowest whole number of moles and gives the relative number of atoms of each element present. Empirical formula. And then we have another one called molecular formula. Shows the actual number of atoms of each element in a molecule of the compound. Now we all know hydrogen peroxide, H2O2, that is the molecular formula of H2O2. Now the empirical formula of H2O2 would be the simplest formula for a compound that agrees with the elemental analysis. It shows the lowest whole number of moles and gives the relative number of atoms of each element present. Now for H2O2, what is the smallest ratio between hydrogen and oxygen? If you divide both of these by 2, that would be H1NO1. Right? So the empirical formula of hydrogen peroxide would be HO. That is what we normally find from elemental analysis. And the molecular formula, the actual molecule, exists as H2O2. So this one is called molecular formula, whereas this one is called empirical formula. Okay. So basically, do you see that the molecular formula is a whole number multiple of empirical formula? Basically, if you multiply this by 2, you get this. Okay, it could be sometimes 3, it could be 4, depending on the molecular formula. Okay. Now let's see how we can determine empirical formula from amounts of elements. Normally in our example where we have hydrogen peroxide that says H2O2, or we can consider water as H2O, these numbers H2O2 and then oxygen has 1, but we normally don't write it. So these ratios 2 to 1, they are molar ratios, meaning how many moles. Okay, and they are normally in whole numbers. We don't see fractions, right? Those are whole number molar ratios and they are not grams. So what we need to do is we need to find out what is the whole number ratio between the two atoms to find out the empirical formula. Same thing here in H2O2. These 2 and 2 represent the whole number molar ratios, not grams. Okay, and they are all in whole numbers. We cannot have fractions. Now keeping in that mind, a sample of unknown compound contains 0.21 moles of zinc, 0.14 mole of phosphorus, 0.56 moles of oxygen. What is its empirical formula? Now we have zinc, we have zinc 0.21, and we have phosphorus 0.14, and then we have oxygen 0.56. We do have a molar ratio, but they are not the whole numbers. Okay, now we need to convert them into whole numbers. How do you do that? What is the easiest way that we can make sure that at least one of these will become a whole number? You divide each one by the smallest number. Okay, so you take your zinc is 0.21, and then phosphorus 0.14, and oxygen 0.56. Let me rewrite this. So we have zinc 0.14, phosphorus this is 0.21. Messed it up again. 0.21, 0.14, and oxygen 0.56. So these are the number of moles, but they are fractions. So in order to make them, so these are moles, in order to make them whole numbers, we're going to divide all of these by the smallest number. So what's the smallest number we have here? 0.56? No. 0.21? No. That's 0.14, right? So we're going to divide all of these by 0.14. 0.14. So phosphorus is going to be 1, that's guaranteed, right? What about the others? 0.21 over 0.14, that would be 1.5. 0.56 over 0.14, this is 4. Now we have 2 of the atoms having whole numbers, and then zinc is 1.5. 1.5 is right in the middle of 1 and 2. So we cannot round it to either 1 or 2. So what you're going to do if you are in a situation like that, you're going to multiply the whole thing by a number that would give it a whole number. What's the best number that we can multiply all of these 3 moles? 2, right? So 2 times 1.5, 3, 2, 8. Now we have a whole number multiple, smallest whole number ratio, zinc 3, P2O8. So the empirical formula would be zinc 3, P2O8. Excuse me. Okay, that's how you calculate the empirical formula if you are given number of moles, but they are not the whole numbers. This is how you convert fractions of moles into whole numbers. I kept this space also to do the calculation, but we don't need it. Okay, now the next one. So it's not going to be easy like that all the time. So it was easy. We were given number of moles. Now let's see if you are given grams. What's going to happen? Analysis of a sample of ionic compound yields 2.82 grams sodium, 4.35 gram chlorine, 7.83 grams oxygen. What is the empirical formula and the name of the compound? So we have space there also. Okay, so first thing you're going to do is you're going to write down the elements. We have sodium, we have chlorine, and you have oxygen. And then the sodium given to us as 2.82 grams and chlorine 4.35 grams and oxygen 7.83 grams. Now, can we go ahead and divide this by the smallest number? No, because they are in grams. Now we need to convert them into moles because the moles will give us the molar ratio. How do you convert grams to moles? You know that now. Using the molar mass, right? Grams to moles. So the molar mass of sodium is 23. So 1 mole of sodium is 22.99 grams. So this will convert sodium grams into moles. So 4.35 chlorine. How do you convert chlorine into grams? Chlorine, that would be 1 mole chlorine is 35.45 grams. So you basically divide by the molar mass to find the moles. And then how do we go about oxygen to find the number of moles? 7.83 grams. 1 mole is 16 grams. That's the molar mass of oxygen. So you divide it by molar mass of oxygen. So this will give us the number of moles. This would be 0.123 moles. And then this would be again 0.123. And then the oxygen would be 0.489 moles. Now by using the molar mass of individual atoms, we converted them to number of moles. Now you know what to do next. You're going to divide all of these by the smallest number ratio. Smallest number of moles. Smallest number of moles. 123, 0.123. Divide by 0.123. So this would make it 11, and then the last one would be 3.98, which is more closer to 4. So we can round it to 4. So we got our ratio NaClO4. Okay, so we have the ratio NaClO4, 1 to 1 to 4. Now what is the name of this compound? We know that this is sodium. What is this anion? ClO4, the highest oxygen content in oxyanion, that is a perchlorate. So sodium perchlorate. That is how you find the empirical formula if you are given the grams. By using the molar mass of individual atom, you're going to convert it to number of moles, and then you divide by the smallest number of moles to find out the whole number ratio. Okay, that's how you find empirical formula. Now remember, we talk about that the difference in the molecular formula and the empirical formula is the whole number multiple. Okay, the molecular formula gives the actual number of moles of each element present in 1 mole of compound. Maybe I'll stop here for the other session, otherwise it will not upload to YouTube. So let me stop here.